Okay guys, this is Unit 2, Video 2, Angled Projectiles. Alright, so today we're going to focus on projectiles where we have initial velocity in x and y. If you recall from last lecture, we just did horizontal velocity, and so the v initial and the y was 0 all the time. So that's not going to be the case anymore. This is going to involve some trig, so you may have to go back and review that a little bit. But hopefully we can get enough review in here that you'll be okay. So we're going to solve for those types of problems today. I'm going to zoom in on this just because it's really, really tiny. Okay, so we're going to go ahead and review some trig here. Okay, and what you need to remember is your SOHCAHTOA. If you've never heard of that before, this is a way of remembering how to solve for a right triangle for the sides and the angle when you have sine, cosine, and tangent. So if you remember, this is sine means opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. So I'm going to write these kind of out over here for you. So sine theta is, let me smooth over, opposite over hypotenuse. We'll go through those pieces. Cosine theta is adjacent over hypotenuse, and tan theta is opposite over adjacent. Okay, so that's what you have to remember as we move over here. When we're looking at a right triangle, the hypotenuse is always the longest side, okay? And then the adjacent and the opposite really depends where the angle is. So right now where the angle is here, the adjacent side is the side that also touches that angle, okay? And the opposite side is just exactly what it sounds like, the opposite side of the angle, okay? So hypotenuse, adjacent, opposite. In this triangle, the angle's here. So adjacent, opposite, hypotenuse, okay? So when we solve these, so here we're looking for this side, okay? We have the angle and we have the adjacent side. So what you want to do is you want to figure out, I have the adjacent side, I'm looking for the hypotenuse. So you want the trig function that uses the adjacent and the hypotenuse. So that one would be cosine. And then when you set this up, you'll go cosine theta, which is 20, equals adjacent over hypotenuse. And then you'll solve. So in this case, you need to basically multiply by d to both sides and divide cosine 20 to both sides. And so you should be able to get 12 divided by cosine 20, and you get 12.8. The units will always match what's on the triangle already. So since this 12 is in meters, that means that this side is going to be measured also in meters. Okay? Something that a lot of people make mistakes on is they'll try to use a distance to find a velocity. You can't do that. If you have a distance on one side of the triangle, then the distances are given on the other sides of the triangle. Okay? If you're given velocity on one side, then the other two sides are going to give you velocity. You can't mix them up. B, you have the adjacent and the opposite, and you're looking for the angle. So adjacent and opposite, okay, or backwards. So we're going to use tan theta equals opposite over adjacent. Okay, and when this happens, when you have the angle kind of stuck in this tan function, this tangent function, you're going to actually do the inverse. So theta is going to be equal to inverse tangent of 12 over 14. This should be review. If it's not, you need to come and see me, or you need to review your trig functions. But when you plug this into your calculator, it's going to be this inverse tan. So it's usually the second function button, tan. So the second function, 12 divided by 14. And you get 40.6 degrees. Let's try this one. Zoom in a little bit more for you here. Okay. All right, so we've got 52 meters per second on the hypotenuse side. We're looking for Vx, and we're looking for Vy. This is most typically what you're going to have to do during these problems. So this picture will look most familiar. You have the angle, you're looking for any one of these two sides, so it really doesn't matter which one you look for first. I'm going to look for x, which is the adjacent side. So adjacent, and I have hypotenuse, so that's going to be cosine. Oops. Equals adjacent, which is the Vx, over the hypotenuse, which is 52. And if you do 52 cosine 30, you get 45. Since we're measuring in, this is a velocity, that means that our result will be a velocity. For Vy, we're going to use opposite and hypotenuse, so sine 30 equals opposite over hypotenuse, and 52 sine 30 gives you 26. So those are your two components. Those will fit into your XY chart when we start solving projectiles. Okay, go ahead and give part D a try on your own, and then I'll just give you the answer here in a minute. I'll do it at the same time. Okay, so you're trying to find the angle and the V here. The angle, I got 56.3. If you're not getting the same thing as me, make sure that your calculator is in degrees, not radians. Okay, you should be in degrees. And then for the V, I am going to use Pythagorean theorem. So no more tan, sine, tangent stuff, just use Pythagorean theorem. So 8 squared plus 12 squared. And then square root that answer. So I got 14.4, and we're in meters per second. Okay. If you're having trouble with that, please come see me, because we're going to skip right past that now, and things are going to get a little bit more difficult here. All right, couple notes about vectors. This isn't super important at this moment, but I'm going to go through it, and then it will come back up. Vectors are arrows that represent quantities with direction, so numbers or amounts with some direction. For motion, a vector can represent displacement, velocity, or acceleration. Those are the three vectors we've been working with. And today we're going to use them to represent velocity. Vectors can be added together. This is the part that isn't as important right now, but we will see it later, so I'm going to just kind of quickly go through this. Two vectors can be moved without changing the direction, so you can take a vector, pick it up, and move it anywhere else. Okay, as long as it stays in the same direction, it stays the same length. The sum of the two vectors is simply the diagonal. So if you took this vector, you put it on the other side here, then you would end up with that same vector that you see here. Don't really worry about this part right now. We're going to kind of skip past that. The thing that you do need to know is that a vector, its length tells you how much, or how many, or how long, or how fast, and its direction tells you direction. Okay? Anytime we see a vector at an angle like this, we want to break it into x and y components, meaning horizontal and vertical. So anytime we see this, we're going to take from the end, we're going to break it into its horizontal component and its vertical component, and we're going to make a right angle. Okay, we're going to make a right angle. You could have also done it this way. Okay, so either way, just make sure that your arrows face the right way. So this arrow I would describe as going up and to the right. So your arrows should go to the right and up. You shouldn't have any down or left arrows. Okay, this one's going up and to the right, so I'll have a right arrow and an up arrow. This will be my x, this will be my y, x, y. And this one, I don't know what happened to its arrow. This one's going down and to the right, so I'm going to have to the right and down. Okay, and this would be x and this would be y. Okay. All right, we're going to do something similar that we did in this horizontal video where we draw the vector components on the cannonball. Hopefully you remember doing that in the last one. Okay, the first one's done for you. Okay, next one, since we are accelerating downward, you'll notice that the y parts get a little bit smaller while the x's stay the same since there's no acceleration there. Okay. At the very top, this is really key, at the very top you only have Vx, because at that point the Vy has become 0. If you can imagine, this ball is going to start fast, slow down in the y direction. It's going to slow down on its way up, and then eventually it will hit 0, and then it will come back down. Okay, it's still moving to the right at this point, but it's not moving up or down at that point. And then as we continue, Vx stays the same, and Vy starts to increase on the way down. Okay, and again, Vx stays the same, and Vy starts to increase on the way down. Okay? All right, let's go ahead and flip that page over. And let's go through the steps and an example here. Okay. Angle projectiles are projectiles any projectile that start with an angle with respect to the ground. Okay, so you'll see that in a minute. To solve, we must first, this is key, first break the initial velocity into x and y components. The initial velocity in the y direction is not 0 anymore. Remember, it was 0 for horizontal, but not for angled projectiles. The steps that you're going to use to solve, first you're going to draw a picture and sketch the path. Then you're going to break the initial velocity into Vx and Vy. You're going to make an xy variable list. I don't know what happened to the t there. Okay. You're going to choose the proper equation. And then you're going to plug in and solve. All right, so let's go ahead and do example 1 here. All right, a mortar, it's just like a cannonball, is fired from the ground with an initial speed of 170 meters per second at an angle of 55 degrees above the horizontal. Let's draw this. Okay, so here it comes. The mortar comes out of this thing. Okay, it comes out at an angle of 55. Okay, above the horizontal. Horizontal's this way. Okay, and it comes out with a speed of 170 meters per second. That initial speed is always going to go on the hypotenuse of this triangle, and then you're going to make the triangle. So the Vx and the Vy, okay? And then as this goes up, it's going to do something like this. Okay, follow some kind of path like that. That's step 1. Draw a picture, sketch projectile. Break the initial velocity into x and y. So x and y, this is the initial velocity here. Okay. Let's go ahead and find Vx and Vy. Okay, and we're going to use our sine and cosine. The kind of nice thing is that anytime you're doing it like this for a projectile in the beginning, cosine is going to be for x and sine is going to be for y. So you can kind of start to memorize that. So we're going to use cosine 55 equals adjacent over hypotenuse. And we're going to use sine 55 equals opposite over hypotenuse. And so then you can plug these in and you get 97.5 for Vx. Remember, these are initial velocities, okay? This is how fast it starts off going. And you get 139.3 for your initial velocity in the y, okay? And you can go ahead and plug those in. So we know that this V is 97.5, and the V initial here is 139.2, or sorry, 139.3. Okay, you know the acceleration is negative 9.8 in the y direction because it always is. The other variables that are here, we don't know yet. And the other variables here, we don't know yet. So let's continue reading and see if there's anything else that they give us. They want to know how long the mortar is in the air, how far away does it land, and what's the maximum height. So they're looking for D, how far away does the mortar land, what is the maximum height, that would be our y direction, and the time that it's in the air. Okay, I'm going to go ahead and pause right now and go ahead and start a new video because I'm running out of time. So you're going to go ahead and skip to part 2.